Okay, we're going to take a look at specifically setting up our free body diagrams to show the forces for problem number 22. So problem number 22 is found on page 540. Okay, and it's actually our first problem in the comprehensive shaft design problems here. Now, as they kind of, explain what they want you to do, you don't need to create a working drawing. All right, you don't need to do that. We're just going to do exactly to the point that we did for each one of our examples. So we just want to make sure that we have the minimum shaft diameters and what we anticipate the actuals to be, bump them up to, like, if you would, basic numbers. Okay, so exactly the process that we have, as well as looking at our procedure sheet. But I am going to start by, instead of at the very beginning, we're going to actually just look at focusing on the free body diagram to create for those front, top, and right sides so that we can get our forces oriented correctly to then go to MD solids. Okay, so then go to MD solids. So just going to scooch this down here. So you'll notice that our problem statement is down here. It says we have a shaft, and we're going to be looking at figure P12-1. Okay, it's part of a drive for an automated transfer system in a metal stamping plant. Gear Q delivers 30 horsepower to gear B, and sheave D is going to deliver the power to its mating sheave as shown. The shaft carrying B and D rotates at 550 RPM. Use SAE 1040 cold drawn steel. Okay, so what we're going to do is we're going to look at that illustration, and it's found, we have to go back to the beginning of the problems. It's going to be found on page 536, and it's right here at the bottom. So the shaft that we are focusing on is this one right here. Okay, so this is, if you would, like a front or a side view of it. You can see a pictorial down here, so our shaft is running through here. The gear at B here that's on the shaft is this gear right here. Okay, and then the sheave that they're talking about at D kind of rotates and goes back. And so we show it in this orientation, show it in that orientation. This would be the right side view, if you would, and it's at a 40-degree angle from horizontal. Okay, so let's make sure that we can, along our shaft here, this one right here, we're going to determine, what are the forces generated by the gear and that sheave. So we're gonna draw our three views. So underneath, what we want to do is we want to, gotta get a clean piece of paper here. We want to simply do what we did for those last examples. We're going to draw front, top, and a right side view of our shaft. So I'm going to start, and it's a simplified version. So we're just going to, show horizontal line like this to represent points A through D. That's going to be my front view. Up here, I'm going to put my top view. Okay. These are going to be an orthographic projection. So make sure that you're drawing them as such. Okay. Don't do what the book does. I think it's very confusing. And we're doing an orthographic projection so that you can see how things line up. This is a skill that is required out in industry. Okay. A lot of people are going to be sketching and drawing things front, top, right side view. And you're going to have to be able to kind of interpret what's going on. Pictorials are nice, but they're not always going to be available. Okay. When somebody's trying to get their ideas across, usually this is how they do it. Okay. So now what I'm going to do is over on the left-hand side, I'm going to start with, I'm going to call this point A, mark it off in both places. Again, orthographic projection. B, C, and D. And I'm going to label each. So this is going to be my A, B, C, D, D. And then I'm going to label my orientations. As I look at my front view here, this horizontal axis, I'm going to call that the x-axis. Okay. So this is my x-axis. This, looking down, would be my x-axis as a line. And then in the right side view, I'm going to be looking straight down the x-axis. So it's going to be a point because we're like looking down that right side there. Okay. Now my y-axis, as I look in this view, is going to be my vertical. And in my front view, it's also going to be vertical, right? And in my front view, that means that I'm looking down my z-axis as a point, and I just have it, you know, going down point A there. In my right side view, my z-axis is coming out to the left. That would be the positive z orientation. And then in my top view, my z is going to be, if you would, coming down the positive z in this direction. And then my y is going to be looking down as a point. Okay. Any questions about that and seeing that orientation and how to draw that? I would take a full sheet of this, okay? Straight edges or straight, yes, using a straight edge or a scale, you know, to get them. You don't have to draw it to scale, but showing it in an orthographic projection will just make it a whole lot easier. All right, so let's look at it's just like trying to think, did I start the recording? I hope I did. So that you can go back if you need to. So as we look here, A is a bearing. B is our gear. So we're going to be looking for forces there. C is another bearing. And then D is going to be that sheave. Okay. So let's mark our bearings that we don't have to worry about, because remember in MD solids, it's going to calculate those reactions for us. The purpose of this is to draw this out so that we can translate it to MD solids. You're not going to be doing the statics if you would, but we've got to set it up so that we've got our forces identified. So this is a bearing. We don't need to worry about that. And then C is a bearing as well. Okay, so we don't need to worry about that. Let's look at our gear first. Okay, let's look at our gear first. Our gear is at B. Okay. And I think I've got to remember what the problem said. What I need to know is this a driver or a driven gear, right? Because that's going to set the direction of my tangential force. I have to know. So it says here that gear Q delivers 30 horsepower to gear B. So B is what? Driver or driven? Driven, right. Q is driving B. So B is driven. Okay. Good information. All right. So I'm going to, down here, I'm just going to make a note. Gear B is equal to driven. Driven. So now what I want to do is in this right side view, I'm going to show looking down that x-axis so I can see my gears as circles. Okay. So I have to know where is the point of engagement. So as I look down here, so this is a view looking straight down the axis. Q is on top of B and it's straight above. So the point of engagement is going to be, you know, up on the top of it. So I'm going to show, just like doing my circle template here. Okay. So this is going to be my gear B. And its point of engagement, I'm not going to draw the other gear up here, but its point of engagement is right on the top here. So I'm just going to identify it that way. And I have two forces that are going to be generated due to these two gears being in engagement. There's a radial force and there's a tangential force. The rule for the radial is the same. It doesn't matter if I'm driven or driver. The driven or the driver radial force is always going to go from the point of engagement and point towards the center of rotation. So this is going to be going down. Okay, going down. So my WR B Y, or I'm sorry, WRB, that's all that I need because it's the radial at B. WRB is going to be going down. And again, we can move it along its line of action. So it's going to be translating right through the center of that shaft. Okay. Now we can move it along its line of action because of what? This is a statics The principle of transmissibility, exactly. We can move a force along its line of action and it will have the same net effect on the body. So even though technically it's being applied up here, it still has the same effect on the center of our shaft. It translates down, okay? So it's going to be going down. Okay, so that's going to be my radial at B. Tangential, okay, tangential. Now, in this case, they did not specify the direction of rotation. I believe on 28 they do, so you've got to pay attention to it there. But on 22 they did not. So you get to pick it, all right? But once you pick it, that's what it is. So I'm going to pick it to be clockwise, okay? I'm going to pick it to be clockwise. If you picked it going the opposite, that is not wrong, all right? But your directions might be just opposite and we'll point that out, all right? But you have to just pick a value, so, or pick a rotation. So I'm just going to draw this like this. That's going to be my rotation of my shaft is going to be clockwise. Now, since gear B is driven, the tangential force is going to be perpendicular to the radial, and it's going to go in the direction of rotation, okay? So since this is going clockwise, then my tangential force is going to go like this, just like that. VUT at B. That's it. If it is a driver, it would go in the opposite direction as we talked about the last time, okay? If you need to reference this or go over it, the book spends time on it. And you will find this on page 513. Directions of forces on mating gears, okay? And that's right down here, right down there. So 513 if you need that. And I think it goes over into 514 as well, so. Okay. Now let's put those onto our front and top views. So since we have our radial going down right here, when we take this and we tip it up on its end and we look down now the front side of it or the front view of it, our radial force is going to be seen in this view, okay? The tangential force is going to be like in and out of the screen. It's going to be a point. So we're going to draw our radial force at B here going down. Whether you show it pushing down on the shaft or starting at the shaft and going below it does not matter, right? W R at B, my radial force. Now, the magnitude is going to come from your spreadsheet. Okay, the magnitude is going to come from your spreadsheet. We're just showing right now the directions. And then my tangential, as I look at the top view, that is going to point which way? Tell me. Going to be pointing up. Yep. And that tangential magnitude will come from your Excel spreadsheet. Any questions on that? So that's a gear. The other one that we have here is going to be that sheave. Okay. Here's the sheave. The sheave, again, is we're going down here. This is an orthographic projection for this one. So this is a right side view here. So as we look down, we are going to see it going at a 40-degree angle. All right. And that sheave force is going to be along that center line. And it's going to be along the 40 degrees that's here. Okay. So as we look at this, we're going to draw it then. And I'm going to show it like this. Okay. I'm going to call this force SH for the sheave, and the sheave is at D, right? And it's going to go down and to the left, and it's at a 40-degree angle. Okay. Now, because this is not on the X or Y axis, we are going to show its components, right? Horizontal and vertical components. So then what we're going to do is I'm going to show this going to the right. And just for purposes of being 90 degrees apart, horizontal, vertical, we most often call this X component. I know it's technically not on the X axis, but it's how we refer to it as well in the spreadsheet. So I want it to be consistent with that. The Y is vertical, but the X is just that it's 90 degrees to the Y. That's all. It's a horizontal Technically in this one, it would be a Z component, but the spreadsheet calls it an X. So now we need to show those directions in our front and our top views. So the Y is going to come down. So I'm going to show that one again, whether you show it going down this way or just going to show them both from the top going down. This is going to be F, S, H, D, Y, right? So it's this one just moved along its line of action. Doesn't matter which way it goes. And then this one again is going to be showing, if you would, in an upward direction, pushing towards the back. And those are the only forces that we have to worry about on our shaft. Yes. What was it? Yep. So if you look down from a top, well, the other way that you can do this is you can take this and we could do a right side view here, right? And we would take this and we would go 90 degrees to it. Okay. So this is going to be here. This is going to be here. WTB. It's visualizing it. That's what it is. Orthographic projection. Let me think. So if you're looking down on the top view here, maybe an aid that you could do is, I don't know if I can do this. If I show my thumb going to the right, and then when I look at it going the opposite way, I'm gonna like go up this way and it's pointing in the backward direction. I can't do it really good. Are you seeing it? Are you seeing it? Okay.
Go to the front, it's pointing. Top.
It'd be pointing up. Yeah. It's trying to think, is there another way that we could? Yeah, it's just that. It's just, yeah, it's just visualizing it. Yeah, if you would, like this side right here on my right side would be like the back of the shaft. This would be like the back side. This would be the front side. So if you notice, this is pointing towards the back. So up here, this is the back and this would be the front. Does that help maybe a little bit?
Yeah,
Okay, you saw it now? Okay. Okay. All right. It takes a little bit. Take your time doing that. And this is actually a critical step, because if you don't get the directions in the correct orientation, as you know, your shear and moment diagram values actually change. So I always encourage students, if you want me to take a peek at it before you go forward from this point, I can always verify these for you as well. Okay, just to make sure. All right, so that's the orientation. Now, how do we get these values? All right, let's look at our spreadsheet, because there is a way that we can put them in there and you can get exactly what those magnitudes are for the horizontal and vertical components. Not that there's anything that you can't calculate here, but this automates it. So on our sheet number 1, and we're going to go down to, as you know, it starts up here with our input of our shaft information, then it goes to torques, and then here are our gear forces, our sprocket forces, and then down here are the sheave forces. So you're going to notice that we're going to have to know what our torque is at that point. Okay, so you'll have to have done kind of those early steps. And then we're going to need to know what our pitch diameter is of our sheave. In the problem, it tells us it's 10 inches. It's 10 inches. So 10 is going to be here. I'm not going to be able to fill this all in for you, but then you're going to have a bending force, and that's going to be the one that is the, if we go underneath here, that's going to be this force right here. Okay, so it gives us the magnitude of the force that's at the 40 degrees, but we need it broken into its X and Y components. So now what you need to add is an angle of orientation. And this angle of orientation, the note on the right-hand side, tells you to measure from the standard 0 in a counterclockwise direction. So going back underneath, that means our standard 0 degrees is here. So we're going to go all the way around, round, counterclockwise until we get to the 40. Okay. And then that's gonna be what, 320, right? 320. And I'm wondering, I might be able to, so if I do 320, it's not gonna give me my numbers, gives me my angle, but I'm gonna put 1,000 in for the torque. This is not the torque. I just want numbers. If I put -40, I bet you, yeah, I'd come up with the same. So you could do the -40 if you wanted as well. I thought it would probably do it, and it does. Okay. Again, this is not your values. Don't use these as the magnitudes because they are not correct. They are not correct. I just put a torque in so that we could get numbers. So that's how you would get the magnitude for that one. And then as we know, up here on the top is where we get our magnitudes for our gears, putting in once we get past the torque. Okay. See any messages? Any questions beyond that on our problem 22? Okay. Just want to remind you of the things that I would encourage you to do as you're working on these. There's lots of steps, as we know. There's lots of steps. Recall that you have this procedure to kind of lean on for the, kind of for the order of things. It also goes hand in hand with our spreadsheet. So it lets you know sheet 1 stuff, sheet 2 stuff, gives you some hints along the way of where to find different things. So does the spreadsheet, kind of gives you pages and appendixes and figures that you might need to reference. Okay. But then also it lets you know the things that you need to do. For instance, where we were drawing the free body diagram of the shaft. We were already starting at step 8 there for that one. And then once you're done with that, now you're going to go to MD solids. Okay. And there you're going to get the shear and moment diagrams that you're going to need those values to then do your conditions diagram and then ultimately go to sheet 2. Okay. Now, as we talked about deliverables wise, we have these listed down here. As a suggestion, when we were together the last time, I said, maybe if it's easy enough, rather than having all separate files for your free body diagram and your torque diagram and your conditions diagram, I would suggest taking screenshots of those or pictures and then just putting them into that, that third, what do we call it? Summary of results or something, right? The summary results tab, the third tab at the bottom. I've had a couple people do that and it works really nice. Then you have everything all in the same place. So, so if you can make that happen, then it's one file that you upload, for that particular problem. You don't have to do all the other screenshots. Okay. This one's a little long, and that's why I want to give you time here, considerable amount of time at the beginning of class here to work on these problems and then have me available to answer any questions that you might have or, point you in the right direction if needed. Okay, so then I'm going to stop our recording here and then we'll talk a little bit.